Hello, I am Ram Zaveri, and I'm presenting our work Improving Accuracy and Generalization for Efficient Visual Tracking, a CPU-efficient test-time adaptive approach to track single objects in adverse conditions. We are interested in efficiently tracking single objects in adverse visibility conditions. State-of-the-art trackers perform reasonably well when benchmarked under in-distribution datasets such as GOT 10K, Lassonde, TrackingNet, etc. However, they are computationally very expensive and are not really applicable in the wild. For example, a recent state-of-the-art tracking approach, SIGTrack, runs at 0.4 frames per second on a CPU. Additionally, the model is too large to load on an entry-level edge device, Jetson Nano, making the applicability of such approaches impossible in the real-world conditions. Recently, we've observed the demand for efficient trackers increasing for this very reason. However, they have limited representational capacity and are prone to failure when tested on the data outside of the training distributions. For example, a recent state-of-the-art efficient tracker, Mixformer V2S, performs relatively well on the in-distribution testsets of GOT 10K with 58.7% accuracy, while experiencing performance deterioration on an out-of-distribution benchmark AVisT that is meant for tracking objects under adverse visibility conditions. Progress in the tracking community suggests Siamese trackers provide the highest speed. A fairly recent approach, FEAR, operates at 100 frames per second on a CPU. They have a generic feature extraction block that is shared for the template and search. The extracted features are then cross-correlated with the search features, and regression and classification heads process their corresponding outputs. Most Siamese trackers also involve a dynamic template that is combined with the static template before cross-correlation. We leverage this simplistic design and devise a new Siamese tracker that preserves the high speed, reduced memory, and computing requirements of the Siamese family, while improving out-of-distribution generalization to near state-of-the-art level performance. The new additions to the framework have negligible impact on the CPU speed, while improving the accuracy by a magnitude. Specifically, we contribute by making changes to the architecture, adding a dual search region with a dual template setting. We also introduce a CPU-efficient attention block, which we call fast mixed filtration. We further introduce transitive relation laws and a dynamic test-time adaptation framework to amplify the tracking performance in the wild. We validate our approach with 11 challenging benchmarks. As shown in the figure, in addition to a generic dual template framework, we introduce a dual search region framework. This allows the tracker to stay anchored to the initial target representations, while better latching onto its dynamic appearance variations, as the efficient trackers use smaller feature extractors that have limited representational capacity. However, to guarantee these relevant components are amplified, we introduce a new learnable layer, fast mixed filtration. It acts as an efficient filtration method for enhancing relevant components of the combination of the representations forming the dual template and the dual search region. We only utilize one FMF layer that is shared by both templates and search. The figure describes how our FMF block operates efficiently even on the CPU. It is a convolution-based attention framework split between channel and spatial attentions, and reduces the computation overhead by limiting the matrix operations to be broadcasted element-wise multiplications and element-wise summations across the vector. It further utilizes squeeze and excite framework to excite the relevant features, similar to CBOM and PSA. The latency of FMF is 0.4 millisecond on a CPU, which has decreased from the 0.8 millisecond of PSA, while not experiencing any performance loss. By just adding this simple filtration mechanism, we can observe the improvement qualitatively in the figure. GD describes the ground truth, baseline describes the generic Siamese tracking framework, mix plus concat describes no attention, and mix plus FMF describes addition of our FMF block. The filtration illustrates the tracker's ability to form compact bounding boxes around the object in adverse visibility conditions. In order to bridge the gap between the mixed representations of templates and search regions, we employ a transitive relation loss shown in the figure. It is employed between dual template FMF and dual search region FMF and search features as a regularizer. The loss is a cosine distance loss, where H represents MLP heads. We follow a similar strategy shown in a self-supervised learning approach, SimSiam. While the previous components enhance the performance on the in-distribution tests, the efficient trackers still have limited representational capabilities to track objects that do not belong to the trained distributions. We introduce backward-free adaptation for the first time for single object tracking. It has been suggested that the major reason for convolution-based networks to underperform on out-of-distribution sets is the change in the batch norm parameters. Thus, we calculate instance norm for every instance as shown in the equation in top right and update the batch norm parameters with the moving average. Additionally, to update the dynamic templates and search, we employ a simple parameter-free technique shown in the algorithm. We start a counter C that when it reaches, let us say n equals 60 frames around 2 seconds, we compare the current classification score with the running average. If current score is greater than the running average, then we update the dynamic image components and reset the counter. Otherwise, we repeat the test at the next iteration. This strategy gave us reliable performance with minimal delay in speed. In this figure, we show a comparison with an out-of-distribution dataset AVisT, meant for tracking under adverse visibility conditions. We show significant improvement over Mixformer V2S and FEAR in terms of both speed and accuracy. Our tiny model is 3 times faster than Mixformer V2S with around 8% increase in accuracy, while also outperforming FEAR XS by 9%. Please refer to the paper for detailed comparisons on other benchmarks. The table shows how dynamic test time adaptation improves performance compared to the other test time adaptation approaches, meant for classification tasks which were adapted for tracking in our case. The increase in latency is negligible, while increasing performance significantly. The backward-based approaches did not necessarily improve the performance. However, they did increase the latency threefold. The figure shows qualitative performance on AVisT benchmark. We show examples such as tracking a car in haze in a storm, cycling in snow with low visibility, and motorcycle in heavy rain. We compared our approach with the small model S-Tiny with Sphere XS, Mixformer V2S, and Ocean. Note that S-Tiny and Sphere XS both run at 100 frames per second on a CPU. We show how our approach shows consistency with predictions that are also more compact to the object. Here, we present SiamABC, an adaptive and efficient tracker that is ready to be deployed in the wild. Thank you for your attention. Please contact me for more details and feel free to check out my repository for public access of the code. Thank you again.